You have been hearing with increasing frequency and increasing urgency that artificial intelligence is about to change everything, that machines are becoming intelligent, that the gap between human minds and computer systems is closing, perhaps has already closed in certain domains, perhaps will close entirely within years or decades. You have used systems that seem to understand you, that answer questions with fluency, that produce text and images and code that look like the products of minds. You have felt, using these systems, a flicker of something. Call it recognition, call it unease, call it the particular feeling of being in the presence of something that seems, in some important sense, to know what it is doing. And you have assumed, as almost everyone now assumes, that the trajectory is clear, that intelligence is being built, that consciousness or something functionally equivalent to it is either already present in these systems or is an inevitable consequence of making them larger, faster, more complex. That the question is not whether machines will think, but when and what happens after. This is the assumption that Feynman, had he been alive to see what has been built, would have walked straight up to and started pulling on threads. Not because he was hostile to computation. He was fascinated by it, thought deeply about it, helped design some of the earliest parallel computing architectures, but because he had a specific and carefully developed view about what computation is, what the brain is, and whether those two things are the same kind of thing in any meaningful sense. And his view, followed honestly to its conclusion, produces a position on machine intelligence that is neither the enthusiast's certainty nor the fearful critic's dismissal. It is something more uncomfortable than either. It is a genuine open question, stated with precision, about what intelligence actually is, and whether we have any idea what we would need to build to have it. Here is the question Feynman would have asked, and that I want you to hold before I give you the tools to think about it. When a computer produces an output that looks intelligent, when it answers a question correctly, writes a convincing paragraph, identifies a pattern in data that humans missed, what is actually happening inside the machine? And is what is happening inside the machine the same kind of thing as what is happening inside your head when you do those things? And if they are different kinds of things, does the difference matter? Do not answer yet. You need what comes next before you can answer honestly. Let me build the case for machine intelligence first, because it is genuinely strong and it deserves full strength before it is examined. The case goes like this. Intelligence, whatever it is a functional property. It is defined by what a system does, not by what it is made of. If a system can perceive inputs, process them, and produce outputs that are appropriate, flexible, generalizable, and useful in the way that intelligent outputs are, then the system is intelligent by definition, because intelligence is the name we give to that capacity. The substrate, neurons, transistors, vacuum tubes, is irrelevant. What matters is the function. This functionalist position is not fringe. It is mainstream in philosophy of mind and in cognitive science. It has the virtue of being clean and testable. You evaluate intelligence by measuring behavior, not by opening the hood and checking what the machinery is made of. And by behavioral measures, modern AI systems are doing things that 50 years ago would have been called definitively intelligent. Playing games at superhuman level, diagnosing diseases, generating fluent language across domains. If intelligence is behavioral, the machines are intelligent. The problem is that the functionalist position, while clean and useful, hides an assumption that becomes visible the moment you press on it. The assumption is that the behavior is generated by something relevantly similar to what generates intelligent behavior in humans. That the process producing the output has the same structure, even if not the same substrate, as the process that runs in biological minds. And this assumption, when you examine it with physical honesty, is not obviously true. It may not be true at all. If you want to understand how the universe actually works, not just how it looks, but how it works, hit that subscribe button. Let's find things out together. Let me tell you something about what a neuron actually is and what it actually does. Because the standard comparison between neurons and transistors, the comparison that underlies most of the confident claims about machine intelligence, is misleading in a way that has enormous consequences for the intelligence question. A transistor is a switch. It has two stable states, on and off, and it transitions between them based on a voltage threshold. It is fast, reliable, repeatable, and simple. It operates at a single level of description. Input voltage, output voltage, switching threshold. Done. A modern computer chip contains billions of transistors, each doing this one simple thing, coordinated by a clock signal into a deterministic sequence of operations. The intelligence of the system on this substrate is entirely in the architecture, the way the switches are arranged and sequenced to produce complex behavior from simple components. A neuron is not a switch. It is an enormously complex biological cell. It has a cell body, dendrites, an axon, synaptic terminals. It maintains ion gradients across its membrane using protein pumps that consume metabolic energy continuously. It integrates thousands of inputs simultaneously from other neurons, weighting them by the strength of their synaptic connections and producing an output, an action potential, when the integrated input crosses a threshold. But the threshold is not fixed. It changes. It is modulated by the history of recent activity, by neuromodulators flooding the surrounding tissue, by glial cells, long dismissed as mere support cells, now understood to be active participants in neural computation, by the metabolic state of the cell, by proteins that modify synaptic strength in ways that depend on the precise timing of pre- and postsynaptic activity. Here's the analogy I want you to carry. Comparing a neuron to a transistor is like comparing an economy to an adding machine. An adding machine performs addition. An economy involves addition, but it also involves trust, prediction, social dynamics, history, emotion, institutional memory, regulatory feedback, and emergent phenomena that cannot be predicted from the adding operations alone. The adding machine is doing something real. The economy is doing something real. They are not the same kind of thing. And the fact that an economy involves arithmetic does not make it well modeled as a large adding machine. The neuron involves electrical signals. The transistor involves electrical signals. They are not the same kind of thing. And the fact that both produce electrical outputs does not make the brain well modeled as a large transistor array. Do you see what happens? The metaphor of neurons as switches has been borrowed to build a picture of the brain as a biological computer. And from that picture, it follows naturally that a non-biological computer, made sufficiently large and complex, should be able to replicate whatever the brain does. But if the metaphor is wrong, if neurons are not switches, if they are doing something that transistors do not do, then the conclusion does not follow. And the metaphor, examined closely, is wrong in specific and important ways. Stay with me, because this is where the physical argument against easy machine intelligence becomes precise. The computational properties of individual neurons are far richer than the transistor metaphor implies. A single neuron integrates inputs across its dendritic tree in ways that are now understood to involve local computation. The dendrites themselves perform nonlinear operations that were previously attributed only to networks of neurons. The timing of inputs matters, not just their magnitude. Neurons are sensitive to the precise temporal pattern of their inputs in ways that give them a computational complexity orders of magnitude beyond a simple threshold switch. The synapses are not fixed weights. They are dynamic, history-dependent, modulated by dozens of molecular mechanisms, capable of both rapid short-term modification and slow long-term restructuring. The connectivity of neurons changes with experience in ways that involve the growth and retraction of physical structures, axonal branches, dendritic spines, not just the adjustment of numerical weights. And beneath all of this, the brain is a biological system running on quantum mechanical processes. Whether quantum mechanics plays a specific computational role in neural function is genuinely contested. The Penrose-Hameroff hypothesis, suggesting quantum computation in microtubules, remains controversial and unproven. But the molecular machinery of the neuron, the ion channels, the synaptic proteins, the gene expression machinery, operates at scales where quantum mechanical effects are not negligible. The brain is not running on classical physics. It is running on chemistry, which runs on quantum mechanics. And whether this matters for the kind of computation it performs is a question that has not been answered. This is the part that keeps me up at night. Let's be honest about what current AI systems actually do, because the honest description is very different from the description implied by the word intelligence. A large language model, the kind of system producing the fluent, apparently knowledgeable text that has impressed so many people, is, at its core, a system trained to predict the next token in a sequence given all preceding tokens, optimized over an enormous corpus of human-generated text by adjusting billions of numerical parameters to minimize prediction error. That is what it does. It has learned from statistical patterns in text to produce outputs that are locally coherent, contextually appropriate, and stylistically consistent with the kinds of text it was trained on. This is genuinely impressive. The statistical structure of language is deep and rich, and a system that has extracted it at the scale modern language models operate is doing something non-trivial. But it is doing something specific and describable, and that something is not obviously the same thing as understanding, reasoning, or intelligence in the senses that matter most for the deep questions about machine minds. Here is the disturbing implication stated plainly. When a language model produces a correct answer to a difficult question, there are two possible explanations. One is that it understood the question and derived the answer. The other is that its training data contained enough related text that the statistical patterns learned during training produce a correct-looking output in response to the question. These are not the same thing. The second can produce correct outputs in domains where the training data is rich and the question is similar to things the model has been trained on. It will fail, and fail in characteristic ways, in domains where the training data is sparse or where the question requires genuine novel reasoning rather than sophisticated interpolation. And the failures of current AI systems are not random. They are patterned. They make errors that no human with genuine understanding of the domain would make. They confabulate, produce fluent, confident, wrong answers in ways that reveal the absence of the kind of grounding in reality that human understanding involves. They cannot reliably distinguish between what they know and what they are confabulating. They do not have the experience of being uncertain in the way that underlies honest epistemic humility in humans. The outputs look like intelligence. The process producing them is something else. Whether that something else can be scaled or modified to produce actual intelligence, understanding, not pattern matching, reasoning, not sophisticated interpolation, is precisely the question that has not been answered. Here is the visceral consequence I want you to hold. Every time you interact with a language model and feel that you are talking to something that understands you, perform this test. Ask it about something it cannot have seen in training in a form that allows direct retrieval. A novel physical situation, a genuinely new logical puzzle, something requiring the integration of knowledge in a way that has no close analog in text. Watch what happens. Sometimes the system performs impressively. Sometimes it fails in ways that reveal the statistical engine underneath. The pattern of when it succeeds and when it fails tells you something about what it is actually doing. The impressive performance in the success cases is real. The failure mode in the failure cases is also real. A system with genuine understanding would not have the particular failure mode that current AI systems have. The failure mode is diagnostic. It tells you what kind of thing you are dealing with. Now I want to take this to where Feynman would have taken it, which is not to a confident conclusion, but to an honest statement of what we do not know and why what we do not know matters. The question of whether machines can be intelligent in the full sense, whether a non-biological system can have genuine understanding, genuine reasoning, and possibly genuine experience, is not answered by pointing at impressive outputs. It requires answering a prior question. What is intelligence at the physical level? What is understanding? What is the difference between a system that processes symbols in ways that produce correct outputs and a system that genuinely comprehends what the symbols mean? These questions are not answered. They are not close to being answered. The hard problem of consciousness, why there is subjective experience at all, why the physical processes in a brain produce a felt sense of being present rather than running in the dark like a computer, is one of the most resistant problems in all of science and philosophy. Until we understand what consciousness is and what physical conditions are necessary and sufficient for it, we cannot know whether any non-biological system has it or could have it. Feynman's position, extrapolated from his known views on computation and physics and the importance of not knowing things you do not know, would not have been that machines cannot be intelligent. It would have been that we do not know what intelligence physically is, that we should not confuse impressive behavioral performance with the presence of whatever intelligence actually requires, and that the habit of naming a thing does not constitute understanding it. We called the output of these systems intelligence. We called the systems themselves intelligent. We did this before we understood what intelligence is. The naming came before the understanding and now shapes how we think about the thing we named. This is a very old human habit, and it has led us wrong before. Let me bring this somewhere it deserves to arrive, because the question of machine intelligence is not just a technical question. It is a question about what we are. If intelligence is purely functional, if it is defined entirely by behavior, with no residual that the behavior fails to capture, then machines that produce intelligent behavior are intelligent. And the question of machine consciousness reduces to the question of whether the functional organization that produces intelligent behavior is sufficient for consciousness. This is a coherent position. It may be correct. But if intelligence involves something beyond behavior, if understanding is not just correct output production, but something about the relationship between a system and the world it represents, something about the grounding of symbols in experience, something about the felt quality of knowing, then behavioral performance is evidence for intelligence, but not constitutive of it. A system can pass every behavioral test and still lack whatever the residual is. And whether the residual matters, whether it is a real thing or a confusion, is exactly what we do not know. The honest position is this: we have built systems that produce outputs indistinguishable in many contexts from the outputs of intelligent minds. We do not know whether what is happening inside these systems is the same kind of thing as what is happening inside intelligent minds. We do not have a theory of intelligence adequate to answer that question. And the fact that we are proceeding as though the question were answered, deploying these systems, building on them, making decisions based on their outputs, in the absence of the theory that would tell us what we have actually built, is the most consequential instance of confident ignorance in the history of technology. Feynman would not have said, "Do not build these things." He would have said, "Know what you are building." And right now, at the level of understanding that matters, we do not. We have learned to make systems that say intelligent things. We do not know whether they think them. We do not know what thinking is. We do not know what would have to be true of a physical system for thinking to be happening in it. We are using words, intelligence, understanding, reasoning, knowledge, that we borrowed from the description of our own minds and applied to systems we do not fully understand. And the borrowing has made it harder, not easier, to see what is actually in front of us. The machines are doing something remarkable. Let that stand. What they are doing is real and impressive and consequential. But remarkable is not the same as intelligent, and impressive outputs are not the same as minds, and the distance between what we have built and what we would need to build to have built a mind may be vast or may be small, and we do not know which, and the not knowing matters enormously. The most dangerous thing you can do with a powerful tool is mistake it for something it is not. Not because the tool is bad, because the mistake shapes how you use it, what you trust it with, what you hold back, what you surrender. We have a very powerful tool. We are not sure what it is. That combination requires the most careful, most rigorous, most honest thinking we can manage. Feynman called this the pleasure of finding things out. But the prerequisite for finding things out is admitting, precisely and without comfort, that you have not found them out yet. We have not found this one out yet. The most interesting question in the history of technology is still open, and the people who tell you it is settled, in either direction, are telling you something about their confidence, not about the answer. The answer is still waiting. If this twisted your brain a little bit, good. That means it's working. I'll see you in the next one.